then start. Okay. Let's have a little gander at the whiteboard first. So let's do a quick bit of revision because we were talking about this a couple of days ago. And we should probably make sure we are completely familiar with the concept of basis vectors. Okay, so how are you feeling about basis vectors?
Oh, it's slightly better than last time, just because on Monday I watched a video and took some notes.
Mm-hmm.
Um, and I think, yeah, I mean, I think I explained it before, but the confusion. I mean, I'm still confused, but I think the source of the confusion before was this idea. I remember when we were trying to do the circle stuff, I couldn't understand what it meant to move from one coordinate system to another.
Mm.
But I think the little bit of missing link was that if you have a vector, any vector, the way you think about a vector, like 2, 3 or whatever, that is actually implicit, like the way we're doing it with linear algebra for game making, it's implicitly already scaled by x hat and y hat.
Mm-hmm.
And x hat and y hat, the basis, it's forming the basis for, it's basically just saying where can you go in this universe. And so the x hat is the universe of the x-axis, so 1, 0. And obviously there's no third dimension, so that would be 0, 2. But the point is, you can go wherever you want on x. So that's
Mm-hmm.
the x hat. And then y hat is the 0, 1, which means you can go wherever you want on y. So when we have a scalar that we're talking about, like 2, 3, 2 is scaled by x hat, which is, again, was scaled obviously 1 and 0 because like we think of that like normalized, right? Normalized, x hat is normalized and y hat is normalized, but that really means that just literally means that you're talking about a coordinate system, like you're talking about, sorry, two-dimensional space, because x hat and y hat together give you the ability to go anywhere you want on x and anywhere you want on y. So that's where we always are. And then when we need to transform, it's about changing our basis, which when you say it sounds natural, but the idea is changing our basis from theoretical origin based scaling to the not theoretical real world basis of, my client screen, which could be rotated or zoomed or whatever. So, when I was trying to draw lines in origin space, that made sense to me when I was just looking at the picture where the arrows are supposed to go, and we're trying to draw our, line across our circles when we're doing, axis theorem stuff. But I wasn't, but it made no sense at all because the basis that we're actually looking at on the screen is not x hat and y hat. It's whatever the current scale transform, zoom, whatever, rotate, transform, scale, rotation thing, view projection
Mm-hmm.
that we're actually looking at. So that's why it was completely wrong. Does that mean that, I understand why it's wrong? Does that mean that I could do it from memory right now? Probably not, but at least I have that. I have that. I have that little thing that I know now
That
about basis vectors.
that seems pretty solid. Um, like, I think you definitely got this bit, which was that if you have a vector, you can decompose it into something that uses, this guy and this guy. And I'm pretty sure you basically said that, when you transform a vector, you can set it to equal the same thing. So we take 2 s plus, I won't use s, use u plus 3v Oh, no, I can't use U and V. I hate these things. I use S plus 3T. So I think you did say basically that when you do this, you can take the the original vector and copy that in and replace your two basis vectors with two new basis vectors, and that's the important other transitional step. Is that one is like that's how you transform. So does that diagram make a lot of sense to you?
Yeah, other than I think it's just convention, the v vector tick. That's just vector of some variety. It's not
Yeah.
important.
So that's just convention. So if I have v dash, that's just another version of v. So I could have s dash and t double dash or triple dash or at some point I think you're supposed to switch to like Roman numerals or something.
Right.
It's been a very long time, or possibly it's like maybe
Maybe
like
they already are. No.
maybe it's in brackets. It's like this this notation rarely ever comes up.
Right.
Because
Okay.
usually
Yeah,
it's like,
I get that. Like the thing that matters is that the vector is the component, these two scalar components together in a sense, and you always need to transform it if you want to do something with it by whatever basis you're talking about. And
Yep.
it seems like most of the time we do the basis in the normalized origin world and then move it to the screen when we're done with it.
So we can add a trans. See, this is why I didn't want to use T, because translate. We'll call that R. So if we can modify this formula to add another vector on, and that's just translation. And at that point, we can go to where we were before, which is we've got our line and we've got our circle and we've got another circle, and we wanted to draw like this arrow, so we've decided to say that's our origin. Keep my colors correct. So we've got our origin, and we wanted to draw an arrow that was let's see, so we've got the original arrow was around some other space, and it's what are we doing? We're doing the arrow from there to there, let's say. So we just make that easy to draw. So we've got this arrow there, and then we transform it, so we're moving to this sort of situation with the transform. And then we are adding on the translation at the very end, so we get that business. And so we're just going from basically you might call this and this would be down here, world space, and then you repeat this whole process with our camera for like view space.
That's like zooming.
Yep, zooming, rotating, flipping the view up and down if we're changing between Cartesian and client coordinates, and then projection space when we finally send it out to the graphics card. So each of those transitions, that one, and that one is effectively doing, well, that, but I mean the whole thing. Only it's doing it with the matrix, because as we discussed, these ones here, that one, are part of a 2x2 matrix, and then if we add in that one, we then have a augmented matrix or an affine, a 2D affine matrix when you combine it with the 2x2 matrix. I mean, the augmented matrix is a 2D affine matrix. So, and you remember, if you look at what do we call it, like transform 2D, it's got 1, 2, 3, 4, 5, 6 components, just like our 3 vectors here have 6 components total. So that's revision of pretty much everything we've done up to this point. So is that all making good sense?
On paper, yeah. I don't know. I don't think that with this information, as much as I can understand it, I don't know if I can get from model space to world space. Just looking at the circle code that we wrote, like last time we were writing code, I'm having a hard time seeing. Like, to me, like, I mean, I'm looking at it right now, and to me, I can't see the difference between model and world, because model, I guess, I mean, A and B are in. Oh, wait a minute. A and B are already in world space because these are positions of things in our world, and then when we normalize it, N becomes the model space. Sorry, the model space, right?
No. So N becomes our N is effectively S in this scenario, and P is effectively T. So they become not so much the world space, but this transformation from model space into world space. So
okay.
let me draw this a little bit bigger.
Go ahead. I don't understand normalizing though, so to me it's like going back to
sorry.
Go ahead. No, go ahead.
Okay,
we're having latency fun.
Okay, I'm gonna redraw this red one a little bit bigger. Let's actually say okay, and then we have an arrow, and I'm going to draw it up here like this. Now this arrow, let's see, it's basically got 2 points. I'm just going to draw this one again too. Hang on. I'll draw it slightly differently. But we've got, our circle here. So this is the green one plus the blue one. Let's do it in a nice middle color. We'll call it cyan. So that ends up being over here on the, in a place that we can put it on screen through this process, but we're just here for now. And so we're drawing this. So you recall, if we actually run our program and we stick some circles down, it's actually offset a little bit from the baseline. So let's talk about what the basis vectors are, obviously, because those we got pretty well sorted. So we have the origin is here, obviously. The translation is here. The basis vectors are here, and that's n hat, and here, and that's p hat. Now the fact that they're hats are not particularly relevant, because we could jump into this code, where have I put this code? There it is. We jump into this code and be like, times 3, and times 3, and look, they're not normalized anymore, they're some other length. The whole thing still works, but obviously the size is completely stuffed there.
Right.
But maybe we wanted that. So the whether or not they are actually unit length is not really relevant to this particular thing that we're doing here. It's relevant for some other things because it's like, well, they're unit length, so we know that we're not scaling basically, but we could scale if we were inclined to scale. So that's our P and our N. So what we have over here, I'll use maybe pink for this, sort of purpley pink. Okay, so over here we have our what we're going to call model space, and we basically have 2 points. We have that one and that one, and we'll just focus on the top of the arrow for now. And what that is it is going out some distance on the x-axis. So it's like question mark times x hat, and it's going some distance up on the y-axis. So it's something times y hat. And so let's find out what these are. These values, we can go back to our code. The x hat, well, what are we doing down here? We've got a. Oh yes, so hang on. We also have a is our origin. So, and that's just some vector from wherever the world origin is out to get out to there. Okay, so hopefully a makes sense. Yes. Mm-hmm. Cool. So we have a. Now we have n and we have p, and we're multiplying things by it. And so what those things are, and we're actually looking at this one, the pointy end of the arrow. So that's a end and thickness. So we come back into here and we have purple. This is a end, and this is thickness. So those are forming our input vector. So I can draw this like that. So this arrow that I just drew there, like that one, is equivalent to this one in this diagram that we were considering when we were doing this process. So it's just a vector that we're using, and obviously we can do this multiple times because we also have the thickness thing is more or less the same everywhere, but we also have that's a start and thickness, and then over further on we have b start and b end by b start neg thick and b end thickness. So we have 4 vectors in fact that we're using, and we're doing the same transformation process to them. So we're moving them all into a new space, and they're moving together as a single unit. So is that making sense here?
Mm-hmm. It is. And just to complete it, we're not R is not involved because that's not at this level because we haven't gone to the views yet. Right?
So R, I've kept the colors matching up. So R in this example is the same as A in this example. So A.
Oh, that makes sense. Yeah, because we're translating from the origin to like that spot, that circle is going to be like just in the world.
Yep.
Okay.
Yep, that's.
And so the plus R in our code. Well, I guess.
Well, we've just changed it around.
Added it to both sides. Yeah. Right.
So if I wanted to make it exactly the same, I'd take that A and just be like plus A.
Right. Of course.
Okay. So that's what that looks like, and as we discussed, if we go into transform 2D, this is the same thing decomposed into X and Y. So.
In the vector there, M11 and M12 are the coordinates of the affine transform location in the 3x3 matrix you created by augmenting the two together.
So
It's right 6 by 6, or wait, is it?
So okay, this is as I was saying. So this bit of mass here has 3 vectors or 6 components, and if we go back to here,
That's
we have
going to have
1,
6
2, 3,
components.
4, 5, 6 components. So if we want to think of these as vectors, we have the one we multiply by x. So that's this 2 in this case was originally 2 on the x-axis. That's one vector. So that's S vector, and this one would be T vector, and this one would be R vector, because they're componentized in this particular writing. Like I could write this like result equals v dot x times left plus v dot y times up plus translation. So this is the same, this line is the same as this line as if I had the left up in translation vectors.
Okay. What I was looking at was on my screen here, like, because you
Yeah,
saying
switch.
affine,
Yep.
you saying affine made me remember that we were storing these x and y, like, but we're not. We're storing these to make our 6 components. And I remember that property of affine, but I was wondering why we didn't use x and y in this case. We're using our own x and y provided by. Oh no, here we are. Yeah, we are. They're at the end. I can see them now. They're literally at the end of the transform there. That's the R in this case.
Yes.
I can see it clearly.
So
Okay.
what we could do, in fact, why don't we do this while we have this open? So we remember, public vector 2 left. Get new vector 2. Let me just double check what they are. So 1, 1 and 1, 2. M11, M12. Don't already have a translate property, do I? No, so that's X and Y, M21 and M22.
Oh, I see. We're just you're just componentizing these.
So we could have switched these around. These could be the actual storage variables, and these could be the actual storage variables, and these could be the properties, and we could write it that way.
Right.
But so that's just showing that these are equivalent. So, and the reason they're called left and up is because the this one's a little interesting to think about. There's like I want to go left. How have we defined left? As basically how have we defined the x-axis in this new basis?
I always think of x forward, like positive is right, but I guess that's just because I've always been in that system, right?
Hang on. No, I just can't tell left from right. This should be right.
Oh,
that's
okay.
just me. I'm just like, I just hold up my hands, left, right, yeah. Up, I've got correct. It's fine.
Okay, yeah, this is more like what we've been doing.
Yeah,
before.
that makes a lot more
X,
sense.
right?
I'm just I'm just mirroring it for fun.
Okay.
Yeah.
And then can you go back to where you were doing the switch of the transform to left and up?
Oh, okay. So this will I deleted that code, but it's like result equals v dot x times left. What have I done wrong? I don't know. V dot y times. What have I done wrong? The same thing. Up plus translate. Okay, so this line of code is exactly the same as these two lines of code when they when it happens. So
You don't want to do it that way just because it's going to be more culverts or whatever.
Well, I don't, would that be a virtual call? It probably wouldn't be a virtual call, but it would be a call. But that should, like, in theory, it should generate...
Hitting the property, and that would still have to hit the backing field in
Yes.
the CLR. It's like a double.
In theory, these will get inlined by the runtime.
Oh, okay.
So, you know, we could in fact do that, and it should output exactly the same code. But it's just sort of nice to, I don't know, pull it apart, because I mean, like we're pulling it apart here, for example, and everywhere else.
Yeah, no, this is more illustrative for me.
Mm-hmm.
So no, I'm cool. I'm cool so far. I mean, that doesn't, like, again, it doesn't mean I'm gonna suddenly be drawing all the things, all the places, but I'm got a little bit more awareness. What did you actually want to do today?
Well, I'll just finish up by, so we've got create rotation right here. In fact, we have create scale, so hopefully you can see how this works. So this is our right vector, and it's you know, well, here's our identity matrix. So it's like here's our right vector is 1 unit on the x-axis. Here's our up vector, it's 1 unit on the y-axis. And so we can go through and be like, well, here's scaling. We just increase the number of increase the distance on the x-axis and the y-axis. So the right and the up vector are being scaled. For translation,
that makes perfect sense so far.
For translation, we've left those all as, you know, unit vectors, but we're shifting around our translation vector. For rotation, you know, we don't have any translation, but we've got this cosine and sine, and hopefully that will be familiar to you, that you remember the unit circle. You know, that if that's x hat, and that's equals a unit vector 1, 0, then if we have some random vector that's doing a rotation like that, we have, let's do this with colors, we've got this distance here is cos theta, and this distance here is sine theta. And so, you know, we've got our x and we've got our y for the first basis vector. So this is this one would be right. We go back here, we've got, what have we got? We've got cos and sine. And then if you recall our perpendicular one, we're just taking, you know, we're flipping these around and making one negative. Don't ask me to remember which is which, but we know we're just, you know, we're creating that one, and so obviously that's going to be, if I draw it properly, it's going to be this business here and this business here. So that's going to be what's that? Yeah, this is terrible. This diagram is very poorly scaled, but basically this this is y is cos theta, and this is neg sine theta, where theta is that. So that should be familiar from our perpendicular operators. So that's that. And if we look at vector extensions, that's perp 90. So neg y and x. And neg y and x. Ta-da! So that's how we do a rotation matrix, is we're just making new basis vectors. So, you know, right and up. So all of a sudden our you know, 2, 3 vector from over here becomes, you know, 2, 1, 2, 3 ish there. So like it becomes that vector out there. So that's
all right.
That's everything. That's basis vectors. Hopefully, save this layer off, and we can refer back to it if we need to, but hopefully that's well understood at this point.
Yep.
Good.
That's all I'm gonna say is yep.
All right.
Cool.
Let's actually finish off our thingy now. So we have this guy, and it draws the arrows. Let me get that out of the way. We have, I think this line of code was back when we were doing it. We had two translations. We had B and A, and then we put everything in the space of A. So we can get rid of that. So here's A, because we know this is the sort of starting point for our blackish arrow. And here's B, and we've got that arrow and that arrow. So, and the important thing here is we generated these arrows such that they are in a one-dimensional space, and then we're projecting that one-dimensional space plus some thickness for, you know, display purposes. Plus this, yeah, not so much thickness, but we use the thickness value to get them off that center line. So what we want to do now is we have these points. We have A start, A end, B start, B end on a 1D number line, and we want to know, based on just those four variables, because that's all we're going to have once we're doing it, you know, in the axis way, whether we've got a collision. So you'll recall that the first time we did this, we basically said, let's do that slightly different, circle and circle, and we basically said, well, let's treat this as, you know, A and B. Let's treat this as a Minkowski style problem and just be like, well, let's just take one massive circle, A plus B as our radius versus a point. And if that point's inside the circle, then we have a collision. If it's outside, it's not. So we're now doing it on the axis. So what we have instead is just a number line with arbitrarily placed, but relatively, like these make sense relative to each other, points. So we have A start, A end, B start, B end. And because of the way we've done this, we actually know that start is, you know, A start is less than A end, and B start is less than B end. And we just happen to know this for this particular case because we set it up that way. So the question is, how do we tell using these four values whether we have a collision? Like, we need to detect. Well, let's just go through and think about this.
Well, the dumb way would just be test if B start is less than or equal to A end. That's just like dumb. And also whether A end is greater than B start.
Okay. So yeah, there's four cases here, and let's see if we can figure out what they are. So we also know that the A center is less than B center, but I don't think that's relevant. That just lets us create this condition, I think. No, actually, it is relevant. So we have this case where they don't intersect. And obviously we have the case where they do intersect, so that would be, I'm going to start drawing them with our colors because that's makes things work nicer. So we've got A over here, and we have B over here. So if that's when they do intersect. Now there's two more cases to consider. So do you think you can figure out what those two cases are?
Oh, I mean different. So okay, don't intersect, do intersect.
There's
overlap completely, perfectly, or is that even the thing?
Well,
I
I
mean,
mean,
that wouldn't matter because it could be different shapes or different radius and all that. So never mind.
Well, you're sort of on the right track. I mean, that case is really kind of degenerate, and in fact, that case is going to cause us problems if they overlap exactly, because we still have to create this axis vector, and I think we're using safe normalize, so it will actually work out okay.
Right.
But
that's not one of the cases.
This is like the fifth case, because this one will decompose into, this one will become one of the other cases. So we should probably actually think about this, because, this is the sort of situation where, using less than versus less than or equal to might become relevant. So we'll think about this one as well, but we'll just assume that this particular case is going to be like a special case of one of the other three cases where they intersect.
Okay.
But you're on the right track. Sorry?
What if they're touching exactly on the edge?
Okay, that's a sixth case. The same scenario though. That's the same situation as.
Right. Yeah. Okay. I just can't get there. Okay. Hold on. Don't intersect. Do intersect. Are we going Schrodinger? They both intersect and don't intersect at the same time.
Not quite. It's they're two different kinds of intersections. So we've got an intersection like this, but there's two other ways they could intersect on.
On the other different axis intersection, right?
Well, I mean, there's only one axis.
We're in a number line now. Yeah, because yes. we've made it that way. Nope.
In fact, this might be an easier way to discover it. Let's go back to here. Let's run our little program, and let's try drawing these out and see what we can come up with. So we've got don't intersect. We've got do intersect. But there's
subsume, right?
Yeah.
One is completely within the other. Yeah, Death Star.
Death Star, yep.
Right.
And there's two different ways to do that. So there's A is bigger, and well, that one's B is bigger.
Right,
and then
right.
A is bigger.
Gotcha. I think you're right. When I was on the right track, I was thinking about them perfectly overlapping, but then I just needed to think about different sizes.
Yeah. I realized, when I was figuring out what we're going to do, it's like, oh yeah, need to cover these cases, and I did it by drawing it in that thing. So let's just draw out cases 3 and 4 over here. So it's important to know what these cases are, because maybe when we're designing our detection algorithm, maybe we have to consider whether those need any extra tests or different tests and so on. So that becomes the question is, how do we program this? So this should be fairly straightforward. So we're going for, now this is where we get coding. This is the fun bit. Let's just say bool sex equals something, and then I don't know, we'll draw a line batch dot line A B, I don't know, thickness pink. So if intersects, we'll just, for the time being, we'll draw our intersection as just like a line that says, do they intersect? So your job now is to come up with that. So using only A start A end, B start B end. So this should be fairly straightforward.
Oops. Start is less blend state. B start is less than A and or A start is A end greater than A. B start. Hold on a minute.
That's the same condition.
Yeah.
You mirror that. It's
I'm confident about this.
confident. Well, shall we test it? I mean, this is one of the magical things about programming. Is we can just hit F5 and see if what it does, and before we think too hard, we can see what happens.
Well, it's because I know B in our world, B is always after A. Oops. Bad things are going to happen, aren't they?
That looks like it's
Apparently.
detecting an intersection.
Yeah, just really not a best color.
That's all right. We'll change that. What color did I use in my test? I had a nicer color for this. I just used magenta. Oh,
Okay.
I used dark red and dark blue as well. That makes things a bit nicer.
Yeah.
Anyway.
Yeah, but visually, right, this is B start, and B start is less than A end, which is here, obviously, so it's going to overlap here. So.
Yep, and now you can see why we used arrows here, so we know which is the start and which is the end very quickly.
That's right, and then, yeah, if we want to I guess we have to cover the fact that B could. Well, I guess B could never be over here, because if it was, well, hold on. Yeah, it could be over here. So.
But you'll notice our axis is spun around. So in the axis space, B always comes after.
Okay, right. So then the only one left. Okay, so I have this. I have this guy. And, anyway, that's it. I mean, when would it ever be over there? Because we're just gonna flip around.
Yep.
So I think we're good for that.
So there's two other cases we need to test. Shall we test those?
Sure. Well, I'll do the cheap one. Go ahead.
I was going to say, come back into the testing program because we need to test that.
Oh, right.
And that. And they look like they work with that single test.
Okay. Well, are we done?
I think. Well, I should have let you keep going to see if you got to that point because you were actually still going and I interrupted you, unfortunately. But
that's okay. Well, let me go back then. I just wanted to change the color. So
magenta looks good. Well,
the one weird thing about Death Star, this doesn't look 100% right. This doesn't look right to me.
Well, we're just drawing a line between their centers for now, so that's going to be part of deuce.
Yeah, I kind of want to draw the line from B, or the little guy start to the little guy end. So, I guess we already have that blue line.
Okay, so
I want to know how much we penetrate.
Exactly. So this is where the separating axis theorem comes in, and that is we have two circles that are intersecting. We want this vector here. Well, we want the vector, that takes us out of the intersection. We call that the what is it? The minimum separating axis. Minimum separating something. I've blanked on what it's called. It's called vector. Because you can imagine we could separate these circles, for example, by saying, well, we'll go twice the radius on the x-axis and twice the radius on the y-axis, and if we move one of the circles that far, we're guaranteedly separating them. But obviously that's going to not work for our collision purposes. We want to just separate them by the smallest amount possible, so we want the minimum separation vector, which happens to be the same as the amount that they're overlapping. So fast forwarding a bit to what we'll do in the future is, if we have two squares that overlap, you can imagine that we might have we might be testing on two axes, and we might have this distance here on that axis and this distance here on that axis. And if we want to separate them, we want the minimum one in most cases, because we want to just pop him out that way, not pop him out, this longer distance that way. So we're using this is why we take the minimum separating vector. So in these cases, this one is obvious. It's just that.
Right, it's B, or it's A n minus B start.
Yep.
Right, okay. So
now,
but it's not that, it's not going to be that for the other one.
Well, let's program that in, because like what happened with this one, maybe we'll see that these are actually just the same as this case.
Right, yeah, exactly. That's kind of what happened last time.
Mm-hmm.
Right.
So
okay,
so
what I want, so I want a vector.
Now, before we go too far, I'm just thinking how we want to do this. Oh, actually, no, we'll go with the if intersects thing. I think that's fine. I'm just trying to, let me check my notes. Yeah, okay. So we want to know the separation.
Daru? Oh, A and B. These are floats.
Actually, we want to draw the separation. So why don't we draw? Well, we'll do both. Let's draw out from B start to A end.
Yeah, I thought I was going to do that. Maybe I'm just... Oh, I just need to arrow it.
Yep, so let's grab one of these suckers. I'll let you do that. So we're going to draw from A start to B end, and in a nice color.
There we go.
That's looking pretty grand. We can get rid of, we can stick it in the middle and all that fun stuff. So I'm just going to get rid of the thickness, and that other
I want to get rid of,
line.
Wait. I wanted to get, that's the plus thickness, and that's the thing that's making it go above. That's what I want to get rid of. I don't necessarily even need the other line,
Yep.
Okay,
So now you're going to get a compile error there. Oh my god. Oh no. So what you just missed there is you've got by keys to left. So when you took out the thickness, instead of going, what really happens sort of mathematically is, thickness 0, and then you've got 0 times p, so you have to get rid of the whole term.
Oops.
But yeah, I almost wish that was a compile error, because vector times vector is almost never correct. Like, I'd rather that was a method in the rare case that you want it. I think it's called
Yeah.
a Hadamard product or something.
Right, and it's just there to confuse beginners.
I've made an error. What have I done? I've got my start and my end backwards. So that's looking pretty good to me. So you've got the minimum separating.
So let's see what happens. Yeah, let's test the. Oops, no. Let's test the Death Star. Well, Death Star works.
That's
where's
pretty
the
good.
other version of it? This is reverse Death Star. I'm not really sure what happened here. In this case, we're drawing the whole thing. I don't want to do that, do I? Well, wait. I don't know. Actually, know what's correct here. Like if B is bigger, it's not actually overlapping. This isn't minimum anymore. This is actually too much, right?
Well, let's think about what this vector is doing. So why don't we, look at the case that I have on my screen, or draw it out. What does this vector represent, is the question.
The blue vector.
So, well, I'll make my color the same as yours.
Oh, yeah, right.
So this dark one in here, what does that represent? What does that quantity mean?
That's the amount of overlap and also the minimum separating distance so that they're not overlapping anymore. If I translate B by that amount, they'll be not touching each other anymore. Or not intersecting, I mean.
Correct. So let's draw these cases out. So we've got this one. We're moving B by that amount. They won't intersect.
Right.
If we do this, we put B inside A. We're moving B by that amount.
It'll still
be. It won't intersect.
Wait, hold on. Go back. Sorry. Can you go back?
Yeah. So we're putting B inside A.
Yeah. If I move B that amount, it's still going to be inside. Won't it?
No, because think about it. This rear of B is going
in the
all
center,
the way along there, so it's not going to end up out here, more or less.
Okay.
Does that make sense?
I just don't see it, even though I should see it. Like, I know it starts at the center and then it moves that whole amount, but it still looks like it's going to be inside. But I'm now like looking at my screen with a ruler, basically. A piece of straw, and then I'm going to move that over here. It makes sense if I'm starting at the edge.
Well, think about it.
Oh yeah, but that's how much distance. Of course,
Yes.
yeah, that's how much distance it is. Yeah. Sorry, I was thinking about. I was actually subtracting the radius. Half diameter.
In fact, we can draw this. We have the technology, so
we can make it better.
Exactly. B star plus B. What is it? B what is B radius? Circle B dot radius. Circle B dot radius, and so we're just shifting down by circle B dot radius. So we're not doing anything terribly exciting here, but now this might make this diagram make a bit more sense. So does that help you?
Oh, hold on. So let me draw. I don't know if you did something. You did add a feature that I didn't have.
I just moved my. Yeah. See, what
you ended up with it.
What you've done is you've only moved one end of the arrow over here. I've moved both ends of the arrow. So the arrow stays the same length because I've moved both the start and the end of it.
I've got to get my edit and continue rocking again because this is a little painful.
Yeah.
Yeah, A end plus circle B radius. Yeah, there it is.
So it's kind of unclear in that drawing, but
oops. only get one shot. Yeah, okay. Oh, well yours is still prettier because yours actually puts a circle there.
Oh, I drew that by hand. Like,
Oh, okay.
add another circle on yours. Like, it's the features there.
Whee! Right. Yeah, it doesn't do anything after the first two. Okay, cool. Yeah, it makes perfect sense there. Now we still have another thing to test though, right?
Well, before we test that, let's back out this change because
Yeah, I don't need it anymore.
that's going to actually get confusing. Because the thing is that's not the values that we're working with.
Oh. Daniel learns all about distance again.
Oh, it's all right. Distance is good to know about distance. So yeah, we were satisfied that this vector is actually moving, the rear of B outside of.
That's right.
To the outside.
Yeah. Actually, it's easier to see when it's smaller. But yeah,
So and we did this case. We're satisfied that one's correct. It's moving end of B to the outside of A. And then obviously this one's not intersecting. So the last one was, yes, B is bigger than A. So now if we think about what that arrow means.
it doesn't mean what I want it to mean. It's not the minimum separating distance anymore. Wait, hold on. Maybe it is. Wait, so which one is A? A is the little
red.
one.
A is the little one.
So this is how much does A have to move to get out of B?
No, because remember what our arrow means. Like if we look at this case, what does our arrow mean? It means
the distance to get
moving B the end of B out of A. So
it's still that.
If we do that, yes.
So it's the distance to get the end of B out of A. And is it not going too far here?
Well, it seems that way because physically you'd think, well, wouldn't you move the smaller thing?
Right, but we want to move the bigger thing. Just
mathematically, like like in our scenario, neither of these circles have any weight as such. It's purely mathematical. Later on,
right,
we might think about what it means to give them some weight. In fact, in a few minutes, we will be doing that. So we'll at least be looking at that. But for the time being, does it satisfy you that arrow still means exactly what it meant before and it's correct?
The blue arrow to move B out of A. Yeah, I guess so, yeah. Mm-hmm. It still looks like too much, but it's probably the same. Looks like too much as last time.
Well, let's make a minor adjustment here. Let's say, let's do this.
Oh, I see it now. I see it. Yeah, I see it. I'm good. It's just because I'm forgetting that B is large, so it needs to travel more because it's going to overlap on the back half as we go. Yeah.
So you'll notice what I've just done there.
No, what have you done there?
I'm gonna overrule your color selection. So that's not as. Come back here. Okay, that's better. Okay, now I can actually see what's going on. So now you'll notice I've made a modification to this diagram. And you may have seen me coding it up. I'll actually scroll it onto screen here.
Well, you're going you're going the other direction. You flipped A end and B start.
So
now you're going away.
So this arrow means something else because I flipped it around. So I mean,
now it's the distance to get A out of B, and that one looks right.
And furthermore, we can do that. In fact, Let's make this super obvious. Does that look pretty good to you?
Mm-hmm.
Yep. And obviously the same. Then we'll get the same situation when we have like a large A and a small b. It's like this thing is huge, but you know.
But all you're doing, yeah.
So hopefully that proves that this vector is, you know, you can apply it to b in one direction and a in the other direction.
And it'll work out.
So I mean, I'll draw this out because this is worth drawing out. What we can do is we say we've got a circle here and a circle here. We can kind of say that let's draw it in a pretty color. That is what we want to separate. And maybe, you know, we could do it that way. We could do it that way. We could, in fact, split it up and do it both ways.
Right, a little bit of each. That would be more smooth, I guess, if you were doing some kind of ball game.
So if these are both movable objects, we take, you know, half and half and do that and that. Now maybe in our gameplay, one of these is like part of the environment and it doesn't move. And so we have to get the other one out. So we have to then apply 100% of the separation vector to this one that's, you know, a moving object. But
then we'd apply that bit of overlap as some kind of force, right? So it would like appear like it did the thing, like get blasted out.
Just to fast forward to what we'll be doing there. What we'll probably do is we'll separate and use this separation axis because we know, you know, this is the axis on which they collided. So we know that this is like perpendicular to where they collide. So if this one's coming in like that, we'll then do the appropriate force as well to bounce him off like that. So we'll separate him out so they're not touching, but we'll also apply a force in this, or we'll change the velocity in this direction as appropriate to cause him to bounce as well. So we use this for two purposes: one, to separate, and two, to get this axis of collision, so we know how they're colliding.
Makes sense.
So obviously, yeah, if we've got, for example, you know, we could get fancy about this. If we've got like, you know, one big heavy object and, you know, some tiny little object that's like mostly embedding itself in the thing. And we have, I've drawn this a wee bit small, but, you know, we have our separation. Maybe we do it like over here. We could get as fancy as like, you know, this one gets 20% and this one gets 80% of the separation vector. Because it's basically just a distance. It's a directional distance. And, you know, like I've drawn here, it gets applied to, I guess, the whole thing. Like the position is kind of arbitrary. So in fact, that's what we were going to do now. So we've drawn it from the end to the start. Let's figure out what it is. It's float separation equals
I can't do that anymore.
B start minus A end.
Do I have the absolute? These are vectors, though. Wait. No, they're not.
First of all, I'm going to reverse that change that I made so that all of the things are pointing in the same direction, because that makes life easier. Yeah.
I need to abs this, like this kind of junk.
No,
I mean, well, not the
because
way we have it, because we've already done the hard work of aligning it to this.
well, we could abs it, but it is kind of directional, particularly if we start like, okay, so this one is B gets 100% of this, so we actually want it going in that direction. If we abs it and suddenly it's going backwards or something,
Yeah, makes sense.
we'll be moving the wrong thing in the wrong direction.
Right. It's directional, and it's in the sense that we're in right and up world.
Yes. It would kind of work depending on how you did it if you abs it, but best not to, because it actually does have a direction.
Okay.
So, let's have a quick think about what this is. So this is B start minus A end. So did I... Well, I've kind of got it. It's written on screen right now because that would be screen. Let's have a nice screen. So B start is this. B start minus A end is that.
Whoops! It's the wrong way, isn't it?
Yes.
Yeah, that's just dumb.
That's all right. I thought I'd just give you that one because, yeah. You recall our cheat sheets. It's like if you want the, the vector going from here to here, you take that and subtract that. So A end minus B start. And that works in, one dimension as well as multiple dimensions.
Right.
So,
yeah.
A end minus B start. Now, I mean, let's do. Okay, I'm gonna
draw the final destination of where it would be.
Pretty much, separated. But now before we go too far, let's just change that to dark red and dark blue, so I can use red and blue for this, because we will want to. So what I want to do is I want you to draw two arrows, one from A and one from B to, well, it would be B plus, and then question mark. Let's say, what are we doing for thin lines? 2 divided by zoom. Red and blue. So we have our axis. So I'll just give you that. It's we are still moving along the normal. So hopefully that much is obvious. It's like we're always on this line, no matter what our separation vector is. So the question is, what do we do to apply our separation to these things? And over to you.
Sorry, I'm drawing arrows.
Yep. By the way, I've changed the thickness down to 2 because that will make it clearer.
Okay, just here.
Yeah. Just to, because we're going to want it.
But I don't know what you're asking to draw. You want to draw.
Okay, so basically, what we're drawing is these, in this case, these two cyan arrows here. So that one and that one. So we already have a position and we already have a direction. It's like, how big are those arrows going to be? Are they going to be like that big, or are they going to be like that big? And what direction are they facing, and so on. So you've got the start points, so that's A and B, obviously. And you've got the directions, that's N, so the direction is along that axis N. So it's just a matter of how far, and that's the question mark.
Wait a minute.
Mm-hmm.
No, I'm just gonna see what this does. I think I'm missing something like a
That's
negative.
fine. That's fine. I mean,
so where's my red is here to here, and blue is here to here. Well, that's not correct.
maybe 2 is too thin.
I'm just drawing the minimum distance. I think I want to draw. Well, was that what I want? I don't know what I want anymore.
Well, let me jump ahead.
It looks like the little arrows on your screen, but I don't necessarily know if that was. Oh no, it doesn't. The red one is going the wrong direction. So the red one is A. So
let's flip these out into. Well, if you're happy with where this is going, but let's flip this out into variables too, because that might make things easier.
Okay, so yeah, just A move is A minus separation.
Well, A and B are just the center of A and B. So in fact, A and B.
Oh yeah, yeah. Sorry, yeah,
that's all right. We've just moved our vector around. I mean, we could stick the vector at like, I don't know. Well, they could just both be at B, and it'd still be the amount we want to move A and B by. So we could like draw it like that, and it would help if they intersected. And then they could all draw around B.
I did it wrong again somehow. Oh no, because I forgot to cancel the signs out.
So jump ahead a wee bit. Jump to the grand finale, and then we'll fix up the maths.
Oh, good. Fixing up, my favorite.
Because the maths is pretty good.
Okay.
Why don't we draw the new position of the circles?
Now, how come we're applying this to both of them? Because isn't it true that only one of them has to move the minimum distance for them to specifically the B one has to move to make it? But like you said, we're applying it to both sides. But I don't see us applying a half of the separation to each side.
Let's have a little think about. Let's jump ahead. Let's say that we're going to move them by that amount regardless for the time being, and we'll fix it up. So we're going to draw two circles. Circle A dot radius. Circle B dot radius. So just drawing two circles. So the question is, where are our circles going to end up if we move them by this amount? Where do they go?
A's gonna. So new vector. And no, we don't want to. I always think I'm doing so. Every time I go new vector, I think it's something I'm doing wrong. So A plus.
That's a pretty good instinct. I was about to say, new vector.
Don't do that ever again. That's basically what I gotta do. So this has got it. Well, I mean, this isn't. That's the thing. The thing about that is, well, let's just use this separation. Actually, no, because this is already.
Well, I've separated the separation out so that we can fiddle with it up here once we're done. So. Okay.
Well, I know I want to move them by both sides, but this is obviously adding a vector and a float together is no good for anybody.
Well,
so I need to scale this by something, and
sounds great to me.
Old basis in which to scale x and y without having to screw around with the components, because that's always wrong. Because I'm not in that basis. I'm not in some made-up basis.
So we're looking pretty close. Yes. Those two circles have separated, but they've separated by a wee bit too much.
No, exactly double. No.
It looks like exactly double. So
Well, that's because I mean, this is again. I don't know if it's even correct to give two.
well,
To give two.
we know what separation means. It's the minimum distance to. Let's keep our change up to here because we still want to be working on that one axis. This is just for output for the time
Yep,
being.
that's what I'm doing.
Yep.
I'm keeping it inside the thingy. Oops.
Well, sorry, when I say inside the thing, I mean up in this A move thing. But yeah.
Oh, hoisted.
But
Okay, I thought you.
yeah,
Well,
sorry, but I think if you draw that, you'll find that although the arrows are wrong because we didn't hoist it, the circles are correct. So
yeah. Oh, I see. Right, because I didn't. Right, because I didn't move it up. I'm not going to get them in the right spot. Okay.
but it's looking good. It's looking real good.
Let me. How bad is my keyboard sound, by the way?
Oh, it's actually pretty good. I don't know. YouTube likes a bit of keyboard. They probably this microphone probably picks up mine very badly, and it's
yeah, it absolutely does. For sure.
Mine is super clicky, which I love.
But yeah, I have the blues or whatever, the very clicky ones, but hopefully. Oh, it still didn't do the thing I wanted it to do. Well,
did
actually,
it not?
I guess it did.
It did. That's looking very good to me.
Cool. Okay, let me just test not intersecting and reverse Death Star. Cool.
And so hopefully that, after doing all of that work, that shows how the Death Star scenario plays out. It and the reverse one as well. So we could fiddle around with this factor here if we were so inclined. I was trying to think.
Well, I guess it's game specific almost also, because what makes more sense, because you were talking about weights, right? Maybe if one was heavier than the other, it would get a disproportionate.
Exactly. So yes, usually you would use mass, and in that case it would be, I guess in a 2D game it would be mass time. It'd be density times area, depending on how you stored it. But yeah, so I mean, I'm trying to think. I haven't actually worked out the mass for this one myself, so. Because what we want to do is, I guess, yeah. So, float, it's one of those annoying things where it's like I want the ratio to be one and then the other. I know what it is. Okay, so float. I'll just do it straight. I'll do it inline because that's how I think. Circle a dot radius divided by dot radius plus too many brackets. Okay, so this code that I've just slapped together, does that make sense? Yes? No?
I was muted. I was saying it was the. Yeah, it makes sense. It's just you're basically this proportionate weight based on the radius of the whole of both objects. So yeah, the bigger one gets more.
So let's
proportionate to its size difference.
Try that out. I seem to have it backwards. I definitely have it backwards. Yep.
Inverse proportionate to the...
It's correct, I think. Yeah, no, it's correct. It's absolutely correct because you can see this one's moving a huge distance. This red arrow here. Let's move the arrows on top so I can actually see where they are.
Yeah. Oh, yeah.
Yeah, so this blue one's moving a tiny little bit and this red one's moving a whole lot. But here's the thing. Here's where it actually gets interesting because I've used the radius when what I should have used is the area. Now, let's just have a quick gander for what the area of a circle is. So as I was saying, it's, density times area. And it's like, I completely forgot to use it. So it's half pi squared. Yeah. It's pi r squared. But we actually don't need to be using pi because we're using that in all
Even though
cases. Well, it's going to cancel
Pi
out.
Day? It's Pi Day. You got to use pi. It is Pi Day.
Oh, it is too.
314.
It's well, it's in Australia, so I've missed it actually.
Right.
But yes,
Two chances.
it is Pi Day for you. So
That doesn't mean use it. He already had his day in Australia, so you don't have to use it.
well, so what was I doing? Equals so the thing is, the reason I don't need to use it is because I'm about to divide by it anyway, and it should cancel. Maybe it doesn't. Pi r squared. Why not? Let's do this properly. No, it does cancel out because it was pi times r squared, and there's pi divided by pi plus. I don't know. I have to. This is the thing because I'm just slapping this together and I haven't actually sat down and done the maths, but I think it does actually need the pi in there to be correct. So what's that? That's the mass of B divided by that. So in theory, oh, get in there. Now, yeah, okay, and now you see this. This looks like it makes a lot more sense.
Yeah, it does.
So,
yeah, the little yeah, it's very cool.
That's what a little physics will do for us.
That was physics?
Well, we're considering the mass of this object, and so to consider the mass, we need to consider the area. Because I mean, that's why it didn't make sense to use the radius. That's why it gave us a weird result when we just used the radius.
Right.
Because that's like a non-physical thing. So, in so much as this is simulating something physical, I guess.
Yeah.
I guess it's physics. But yeah, actually that's very satisfying actually, because it's like, that now feels about right. So once we actually have masses for these things, like we could say that A is like, the density of A is 1, and the density of B might be really heavy. Like it might be less, if we have like an immovable object, it's going to be infinite. So let's just say we have something really heavy. You'll notice that
Didn't even move basically, or almost not at all.
Even though B is smaller, it's super heavy. So A is the one that's doing all the moving.
Right.
So there's a little bit of physics for you.
Cool.
All right, that was great. Let me grab OBS and we'll finish off. I think we've done pretty well. We've got it working. So we'll see you later, YouTube.